Okay, let's dive right into this incredibly fascinating explainer about how we verify the absolute truths of our universe using strict computer code. Seriously, have you ever stopped to wonder if the complex math physicists use to describe reality is actually unconditionally true? Well, today we're taking those dense, chalk-dusted theories and translating them into a language a computer can unconditionally verify. We are completely removing human guesswork from the equation. We're looking at a project that doesn't just, guess at the laws of physics. It forces them to literally prove themselves through unyielding lines of software code. It's a fundamental shift in how we understand existence. So, how do we prove the universe mathematically without human error? What's really interesting about this question is that it challenges our basic reliance on human intuition in advanced math. For centuries, humans have scribbled equations on chalkboards assuming certain logical steps just because they kind of make sense to our brains. But here's the thing. Our brains are wired for a macro world, not the quantum realm. When we're trying to prove the fundamental rules of the universe, what makes sense to us is heavily biased by our human perception. And that intuition, it can hide some really deep systemic errors. A computer, on the other hand, demands an undeniable match. As the code dictates, it needs to produce an equality between actual ring elements. Now, that's just a highly technical way of saying the foundational building blocks of the math must perfectly mirror each other. A computer doesn't naturally know that 2 plus 2 is 4, right? It requires an explicit, unbroken chain of evidence. There is absolutely zero room for, hey, I assume this works. Every single leap of logic has to be rigorously defined and proven, all the way down to the absolute mathematical bedrock. To pull human error out by the roots, we're actively moving from the realm of theoretical physics straight into the rigid discipline of software engineering. Physicists and mathematicians are using intense, symbolic computer programming to build undeniable proofs of reality. We're transitioning from abstract ideas debated in lecture halls to strict, unforgiving software environments. And the stakes here are incredibly high. If the code compiles and the logical proofs execute seamlessly, the universe's law holds true. If it doesn't, well, reality fundamentally rejects the math, and it's entirely back to the drawing board. Here's our roadmap for this explainer. We'll start with coding the laws of reality, move into the rules of formalism, check out the step-by-step proof mechanics, see what happens when scaling up to physics, and finally, look at achieving mathematical closure. Let's kick things off with Section 1, coding the laws of reality. Think of this process as the ultimate, unforgiving building inspector. If a single logical bolt is missing, the entire mathematical structure fails inspection immediately. This concept is known as formal verification. It's not just punching numbers into a calculator. It's writing a program where the compiler itself checks to ensure your mathematical logic is airtight from start to finish. To put it simply for us regular folks, a human mathematician might just assume a certain variable in an equation is always positive based on context. But in formal verification, the computer demands an exhaustive mathematical proof demonstrating exactly why that variable can never, ever be negative. No skipped steps allowed. Moving right along to Section 2, the rules of formalism. There is a massive, staggering gap between a human writing equations and a computer demanding explicit mathematical proof. Where a human might casually rearrange an algebraic equation, effortlessly sliding variables from one side of the equals sign to the other, formalized code forces the programmer to write out a multi-step proof just to convince the computer that a basic sequence of variables can legally be shifted around. What takes a human brain a split second of intuition requires paragraphs of strict code to definitively prove it doesn't break the foundational rules of mathematics. The rules here operate a lot like a strict legal contract. The computer requires a witness, a concrete piece of mathematical testimony that perfectly validates the code. You absolutely cannot skip a single step or rely on a logical assumption. And most importantly, the system blocks the promotion of a theory if the logic is incomplete. In this ecosystem, promotion is basically the equivalent of reaching scientific consensus. It means giving a physical law the official green light as absolute truth. Simply put, no mathematical witness, no promotion. The theory remains unverified. All right, let's jump into Section 3, step-by-step proof mechanics. Let's look at how this works under the hood. Take the famous Euclidean algorithm, which finds the greatest common divisor between numbers. The code breaks this down into exact mechanical steps. First, it sets up the variables, then formally checks divisibility, and finally executes an inductive step. Instead of human deduction, it repeatedly feeds the outputs back into itself, exhaustively checking every single division mathematically. It grinds through every iteration so there is zero room for an edge case error. We are literally watching the code prove the math with ironclad programmatic logic rather than human intuition. But what happens when things go wrong? The dramatic part is that if the proof hits a wall, it doesn't just fail or crash. It meticulously flags the exact mathematical coordinate of the failure. It might label it as a bad call, meaning a bad column, or a bad row. It's truly incredible. The system isolates the exact atom of logic that broke down. It tells the mathematician precisely where reality rejected their math, giving them the exact coordinates of their human error. Which brings us to section 4, scaling up to physics. This is where it gets really wild. The code groups massive, universe-defining rules into what it calls a physics closure interface. This acts as a literal software checklist for reality. For example, finite speed is a rule that proves nothing travels faster than the speed of light, and ultrametrics define strict, undeniable boundaries for physical distances in space. The computer constantly tracks all of these. If a physicist proposes a new physical framework and it accidentally violates the basic parameters of finite speed, the compiler will literally reject the universe they just coded. Consider the incredibly complex Navier-Stokes equations, which describe how fluids like water or air flow and interact. To prove something mathematically smooth in fluid dynamics, the code acts as a strict pathway. It forces the computer to first definitively prove the basic energy bounds of the fluid. Only when that foundational math is absolutely perfect does it unlock the proto-Seren step, which then proves the fluid behaves predictably on a global scale. It is exactly like unlocking abilities in a video game skill tree, but designed for the fundamental physics of fluid motion. And we see the same strict accounting in quantum mechanics, too. Subatomic particles mix and interact in incredibly complex ways, tracked by something called the CKM matrix. The code acts as an impartial accountant for this matrix. It tracks what we know for sure, like the element lambda, which has been officially verified and promoted. It tracks other elements as leading candidates, and explicitly flags certain elements as mathematically blocked or ungrounded. This rigorous digital ledger completely prevents physicists from jumping the gun on particle physics before the math is indisputable. Finally, let's wrap up with Section 5, Achieving Mathematical Closure. A physical theory isn't considered true until it secures explicit authority tokens. You can think of these as unbreakable digital signatures of mathematical truth. The math requires an exact match to the standard model of physics and total compatibility with deep algebraic frameworks, like the DHR category, which essentially dictates how quantum charges behave and interact. Without a single missing witness, these requirements create an absolute lock and key system for the laws of nature. If the key doesn't fit the lock perfectly, the theory simply is not promoted. When everything aligns perfectly, the system reaches terminal completeness through what it calls the canonical exact chain. That's the ultimate goal right there. This means every single high-level physics equation links backward, perfectly, and without a single interruption, all the way to the baseline axioms of reality. When data successfully hits this canonical chain, it's certified by the strictest logical engine humanity has ever built. It proves the math undeniably and unconditionally matches physical reality. So, if we can formalize the universe into absolute, undeniable code, what secrets of reality are just waiting for the right algorithm to unlock them? I really hope this explainer has shown you how structured coding is fundamentally transforming our absolute understanding of the universe. By refusing to skip steps and removing human intuition, we are quite literally compiling the source code of reality itself. Keep asking questions and keep exploring the code of our universe. Catch you next time.